So here we are, the end of the semester, and in the effort to commit a lot of this to memory, I'm going to go through these massive documents that I've created over the past couple of months and go over basically what is all of synthesis for Organic Chemistry 1, okay? So we're just going to start at the top here and go through each possible mechanism and just kind of do a brief review of what it is and what's happening here. So the first thing that we really learned was something called hydrohalogenation. So what is hydrohalogenation? Well, it can also be called hydrobromination. It can also be called hydrochlorination, okay? And basically what we're doing is we're adding an HBr or an HCl. This can be in one part or in excess, one equivalent or two equivalents. And you can add this, they're going to react with pi bonds. So you're going to react with an alkene or an alkyne, okay? If you add it to an alkene, you're just going to have the Markovnikov's addition. So you're going to add something to the more substituted side like we see on the right here. If you're adding this to an alkyne, in just one equivalent, you're just going to add one Br. Two equivalents, you're going to add both. But you're going to add both of them to the same carbon in what's called a geminal dihalide, which you can see on the right here. So this is how an alkene would react, and this is how an alkyne would react. Putting it here, and in this case, this is a symmetrical reactant, so it doesn't matter which side you add it on. But once the Cl is on, you're going to add that second Cl to the same side. This is where we come into play with these geminal dihalides, okay? What else do we need to know here? Markovnikov, there's no stereospecificity here. There are carbocation arrangements that come into play here also, okay? Again, this is the geminal dihalide, symmetrical, unsymmetrical. You are going to get two different products with an unsymmetrical internal alkyne. I kind of just have the same thing here. Don't confuse bromination with hydroboration, okay? Those are two different things. We don't want to confuse those. All right. Okay. Now we're going to talk about hydration, or the addition of water. This is water and acid, so you're going to see the addition of H2O and an H+, like sometimes an H2SO4, which is an acid, or hydronium, which is an acid, or simply just a proton H+, which is an acid, okay? You can do this with alkenes or alkynes. Also, it's a Markovnikov addition. And if you are adding mercury, it's an anti-addition. But if you're doing alkenes, you're going to form an alcohol here, as we can see in this picture. It's going to be a Markovnikov's addition. So it's pretty easy in terms of, there are carbocation rearrangements here also, so just be careful. If you're adding to an alkyne, you're going to have a Markovnikov's addition, and you're going to form what's called an enol, which will then tautomerize. A double-bonded oxygen. And you'll make a ketone. If unsymmetrical internal alkyne, you will get two products. If terminal alkyne, you need mercury in addition to your water. So this is what's happening with alkynes. You're going to get your OH, which will then tautomerize instantly into a ketone. Now, we'll get to hydroboration oxidation a little bit later. That's going to be a similar process, although it's anti-Markovnikov, so you are going to get an aldehyde for that, okay? Again, this is hydration. A terminal alkyne, we're getting ketones here. This, we're also getting ketones, just adding an OH group, which is then going to, does this tautomerize here? Plus H2O and H2SO4, we're just getting an O. Yeah, and then it tautomerizes into ketones. Okay, so that is hydration on acid. So now we get to dehydration on acid. This really isn't until chapter 10, but it's the exact opposite of hydration. So I feel like it's worth looking into. Now, because we're working with alcohols, we're only working, well, we're doing E1 with secondary and tertiary alcohols. And since E1 is a two-step process that is able to be rearranged, okay? And this basically comes in with all you need is acid, like an H+, and some heat, and you're going to eliminate an OH, and you're going to replace that with a double bond. So this is what dehydration would look like. We can see it's basically the exact opposite of our garden variety addition of water and acid. Okay, all right, moving on. Now we have hydroboration oxidation, which is very similar. I don't think I actually ever wrote a page on that, but it's very similar. It's just an anti-Markovnikov addition. Okay, and hydroboration, I think of like borat, and he is going to be anti-Markovnikov, and he's going to sin a lot. So his stereospecificity is going to be sin. He's going to add to the anti-Mark spot. So if that is with a terminal alkyne, you are going to get an aldehyde. So that's the important thing. If you need to make an aldehyde, hydroboration oxidation is going to get you there. Okay. All right, now we have alcohol addition on acid. I feel like we don't see this one very often, but we just need to remember that that creates an ether. So if you add like a methanol, you're also adding a carbon here. So if you add a methanol like this, you are adding a carbon. If you add an ethanol, you'd add 2 carbons. No stereospecificity here. There is a carbocation intermediate, and it is Markovnikov. We can add carbons here, ether. So this is what this would look like. Okay, moving on. All right, so now we have these 3, which I like to group together. These are all different types of hydrogenation. Hydrogenation eats pi bonds. As simple as that. The simplest one is H2 over a palladium catalyst. All it is going to do is eat a pi bond and replace it with 2 hydrogens. That's all that it does. It is a syn addition. You could see there was a pi bond here, and now it's gone, and there's 2 hydrogens. That is all that it looks like. You're going to have cis products because they're coming in from the same plane, okay? Now, we can do that with alkynes also, and the thing with H2 is that it goes all the way to an alkane every single time. It's such a strong reaction, you can't stop it. So you see here on the left, H2PDC is going to take an alkyne all the way to an alkane, which you can see here, okay? Now, there's 2 different ways you can do this. If you need to eat pi bonds, you can use what's called a dissolving metal reduction, which is NaNH3. And what this is going to do is it's going to create a trans product. I don't think I have the exact answer here. Well, here it is. This is a trans product, and it's also an anti-addition. Or you can use Lindlar's catalyst, which is going to allow you to have a cis product. And these are both going to stop at alkenes. That's the thing. These are great ways to get rid of a triple bond. They're going to act on alkynes. One is going to make a syn a trans and one is going to make a cis, okay? All right. Halogenation is a big one. This is adding Br2 or Cl2 with an inert solvent. I think HBr technically might have an inert solvent too, but you don't really need to know about that. The solvent's important here because if you change the solvent from like a DCM, which is dichloromethane, that's just an inert solvent, if you change that to a water or a methanol or even a sodium chloride, then you're going to have a problem. But let's go over normal halogenation first, okay? Garden variety halogenation, this looks like Br2 or Cl2. If we're adding this to an alkene, it's going to break a double bond and add the halogen to either side on two different carbons. So in terms of an alkane, if we add Br2, it is going to add both bromines because we have bromines here. And this is an anti in terms of stereospecificity because as one bromine comes in, the other one needs to approach from a different plane. As we can see here, you see one going up and one going bottom here. It's an anti-addition, okay? So that's what that would look like. The Markovnikovs doesn't really matter because it's just going to add to both sides of the pi bond. All right, there's no stereospecificity or regiospecificity or selectivity or whatever in that, okay? Now, if we add Br2 to an alkyne, well, with one equivalent, it's going to break that first pi bond and add to two different carbons. Don't confuse this with hydrochlorination or hydrobromination, where you have a hydrogen involved. Also, that's not going to happen. There's no geminal dihalides if you don't have an H, if you don't have an HBr or an HCl, okay? If you add a second excess of Cl2, it's going to look like this on the right, where you have just 4 Cls, you break all of your pi bonds, and that is your result, okay? Now, what you can run into with halogenation is what's called a competing nucleophile. And all you need to remember is that if Br2 is competing with anything remotely like polar, like water, or like a methanol, it's going to lose the fight, and it's going to lose the Markovnikov's position. Because you're not adding the same thing anymore, so Markovnikov doesn't matter, you have to be like, oh, well, if I have a secondary carbon and a tertiary carbon, one of them's more stable, what's going to get the more stable spot? Well, bromine's going to lose. So if it's competing with water, it's going to lose to that OH, and it's going to form an alcohol. And if it's with methanol, it is going to lose, and it's going to form an ether. So you can see what I'm talking about here is both of these products, you can see that there's a tertiary carbon and a secondary carbon on either side of the double bond here. What's going to happen is we're using chlorine in this example. It's losing to water, and you can see here that the OH is getting the tertiary spot. It's getting the Markovnikov's position, and chlorine's like, oh, all right, dude, like, hey, you want the more stable spot? That's usually where I go, you know, in like an HCl reaction, which I know is a different thing, but it lets the OH have the spot. Same exact thing down here with the ether. It lets it have that more stable spot. So this is what's called a competing nucleophile. Specifically when it's competing with H2O, it's called a halohydrin is your product there, okay? All right, so now we're going to get on to epoxidation. Epoxidation is a syn addition, so if you make two stereocenters, you're going to have, they're going to come in from the same plane. There's a lot of different ways you can look at this. To make an epoxide, you are combining an alkene with a peracetic acid, a peroxy acid, a peroxide, an ROOR, or an MCPPA. A lot of different ways you can look at that, okay? But seeing two oxygens next to each other is a dead giveaway that you're working with a peroxide, okay? And it's going to turn a pi bond on an alkene into an epoxide which looks like this on the left here. In this case, we're using a peroxyacid epoxide, looks like this here. It has this oxygen kind of triangle, and that's what's happening, okay? The whole thing with the ring opening that I remember, if there's a hindered side and you're in acidic conditions, your ring will open towards the, it'll open away from the hindered side. So you will erase the bond that is attached to the hindered side. If you're under basic conditions, your ring is going to open towards the hindered side. So you would erase the bond that is going to the less hindered side, okay? Normally that's followed up by workup. So when that ring opens, it will eventually become just an OH and become an alcohol, okay? Okay. Ozonolysis is kind of a weird one. I don't know that he's going to go over ozonolysis, but what happens here is that a double bond is broken, and it's cleaved in two, and the double bond stays kind of where it is, but there's an oxygen on both sides. So you're adding two oxygens for every bond that you break, for every double bond that you break, okay? And you can make ketones and aldehydes. All right, that was all of the reagents from exam 1. Dehydration was not on exam 1, but I wanted to just include it so you know that it's related to hydration as the opposite, okay? Now, there are some miscellaneous things that he threw in. I'm sorry, these aren't from exam 1, they're from exam 2. One of these miscellaneous ingredients that he threw in was the reaction with acetylene or ethyne. They're both called the same thing. And in this case, it's already deprotonated. So you see here this CH3 triple bonded. There's another carbon right there where that lone pair and that minus are. This is a nucleophile. This is a base because it has a negative charge and it's ready to interact with a leaving group like an alkyl halide. And this is a great way to add on to a carbon skeleton. So this would remove a primary halogen, a backside nucleophilic attack, and add 2 carbons to the carbon skeleton, maintaining the alkyne. Now you can have as many carbons as you want attached to this triple bond. This is a great way to add to your carbon skeleton, and then you can break your triple bond with either H2 over palladium catalyst, which would go all the way to an alkane. You can use Lindlar's catalyst if you would like a cis alkene, or you can use NaNH3 if you want a transalkene, okay? Another thing that you can add is a treatment with NaNH2. So what this will do is, if you don't already have a protonated acetylene or ethyne, NaNH2 will deprotonate that. So we can see that right here. Well, NaNH2 actually does a couple of different things. It will remove a proton and prepare an extension of a carbon skeleton. Do I have that gray thing? Yeah. It's actually kind of similar to this. This is like how you would add it on, but that's for sodium cyanide. That's kind of something else. So it'll remove a proton, prepare an extension of the carbon skeleton with a primary alkyl halide like CH3CH2Br. The other thing that this can do, which is kind of weird because NaNH2 is kind of magic, what it can do is pluck off a bromine and a hydrogen and form a double bond. So NaNH2 basically is like a proton plucker. It can take a bromine and a hydrogen, replace it with a bond. If you use NaNH2 and there's 2 bromines, you'd actually get this. You'd get a triple bond. It's a pi bond creator. And this is the same thing. NaNH2 would pluck off 2 bromine and add 2 pi bonds per leaving group. So that's kind of an interesting use of NaNH2, which he did use on an exam, okay? Reactions with vinyl bromine, allyl bromide, and ethyl bromide. These are all ways to add carbons. A vinyl bromide would add 2 carbons, an allyl bromide would add 3 carbons, and an ethyl bromide would also add 2 carbons. But the cool thing about an allobromide and a vinyl bromide is that they're bringing a double bond with them that you can work with, okay? And they have a leaving group obviously already installed, so you can use that bromide as these are electrophiles that can then react with nucleophiles, right? Because it's negative, make it positive. Right, they can react with nucleophiles like a acetylene ion, and you can extend carbon chains that way, okay? NaOH is just a generic base that acts kind of as OH minus. Sodium methoxide is it's just a strong base also, okay? All right, now we're getting into the things with oxidation of alcohols. And there's a lot in this chapter, so let's just kind of go through it. So the first few that we're going to look at, the first one is called chromic acid. So the oxidations that you need to remember are chromic acid, PCC, and a Swern oxidation. And the good thing to know about all of these is that they work on primary and secondary alcohols. And if you add any of them to a secondary alcohol, it's going to make a ketone. So whether you see chromic acid, PCC, or a Swern oxidation, they will all turn a secondary alcohol into a ketone. The way that you can remember that is that when you're drinking alcohol, not for a second should you think of grabbing your car keys. So when you're drinking alcohol and we're oxidizing alcohols, not for a second are you going to grab your keys. So if you see a secondary alcohol, ketone. All right. Well, what about a primary alcohol? Well, they're all going to do different things, okay? Chromic acid is going to make a carboxylic acid on a primary alcohol, and PCC is going to make an aldehyde as well as a Swern oxidation. The way that I remember these, and you can see all these right here. So here's chromic acid at the very top. We are converting an alcohol into a ketone because this is a secondary alcohol. But what about this one on the bottom here? This is a primary alcohol. We are adding chromic acid. Now, technically in the middle, it does create an aldehyde, but that's not really important because you can't stop that. It's going to go all the way to a carboxylic acid. I remember this because primarily Google Chrome is a great browser out of the box, which means if I have a primary alcohol and I add chromic acid, I'm going to form a carboxylic acid, okay? Now, PCC is going to make an aldehyde. It'll basically stop in an aldehyde. And the way I remember that is that primarily I would like all the recipes. All the PCC, all the aldehyde PCC. That's for primary. Even if you forget that it's a primary alcohol, you have already remembered that secondary alcohols, because you're not going to grab your keys for 1 second while you're drinking alcohol, that the oxidation of alcohols make ketones, okay, of secondary alcohols. Tertiary alcohols, I believe, aren't involved in these reactions, okay, for oxidation. Okay, so that's not too bad. The other thing that you could see is oxidation via osmium tetroxide. This is going to add OH groups and create what's called a cis diol, which will look like this. And this is actually going to affect not an alcohol. This is going to create an alcohol, and this is going to affect an alkene. Okay. Triethylamine. Yeah, this is Swern oxidation. So secondary alcohols still make ketones. Primary, they're going to make aldehydes too. So you can think Reese's Pieces, I don't know, you swern, you swerve when you drink Reese's Pieces, when you eat Reese's Pieces, that's going to do the same thing. All right, then there's this triple threat, PBr3, PCl3, and SOCl2. The way I remember these is in Southern California, they drink PBr and eat fried pickles. Okay, they keep it simple in California, and there's no inversions. These are also going to work on primary or secondary alcohols. And they're all going to do the same thing. However, PBr3 will add a bromine, PCl3 will add a chlorine, and SOCl2 will add a chlorine also, okay? Now, these are two successive, and I'm going to show you all three of these. There are two successive SN2 reactions. Now, remember that an SN2 reaction, which happens in one step, and both the substrate, both your alkyl halide and whatever you're reacting it with, are going to be involved in the rate law, that there is an inversion here. However, there's two successive SN2 reactions, so there's no total inversion. So we can see PBr3, PCl3, and SCO-Cl2, how they just gently remove an alcohol from these primary alcohols and replace them with these, with the better leaving group, Br or Cl, okay? It would do the same thing to a secondary alcohol. However, if you are involving a stereocenter and you're removing an OH, oh, this is weird. It's creating an ether. PBr3 and pyridine is going to add a bromine leaving group and then replace it with a nucleophile. So that is where you're going to have a double inversion, because PBr3 will invert once, then the nucleophile will backside attack and invert a second time. You'll have the same configuration as the alcohol if you're working with two things, okay? So just remember that. It'll knock it back into the same configuration. Something called tosylation with toluene sulfonyl chloride will also work on primary or secondary alcohols, but it's one successive SN2 reaction to substitute an alcohol, okay? And you're bypassing carbocation rearrangements here because you're working with SN2, which are one-step reactions. The way I remember this is you toss one SN2 baseball so hard that it inverts the catcher's glove. So if you're working with TSCl pyridine and CH3O-, another nucleophilic attack, you are going to have a configuration here opposite that of the alcohol, okay? So these are like a little confusing to think about, but just remember that that this is what's happening here if there's two things being added. So technically, PBr, PCl, and SOCl2 by themselves, I believe, would invert because it's an SN2. However, if you're following it up with a nucleophilic attack, like a CH3O-, and you're adding these ethers, then you are going to affect the stereochemistry again. Okay, almost there. These are different kinds of dehydrations that we can do. We already did dehydration on acid. If we add POCl3, it forces an E2 reaction for a better yield. So POCl3, I think, is just like a bulky something, I don't know, and it's going to create elimination for you. I don't know how I can remember that. Pockle, you eliminate your pockets in your genes or something, and it's not conducive to carrying things. TCl can also dehydrate and do an E2 type of deal. Epoxidation, this is another way you can make an epoxide, which we've never really gone over. Sodium cyanide is just a way, just like acetylene, where you can add in, add a carbon with a negative charge to it, to a leaving group like a bromine, electrophile. Cotbu is something we use a lot. This is potassium tert butoxide. It's a bulky base that I think is going to favor elimination. Primarily, it's going to favor Hoffman elimination, which is going to be kind of like an anti-Markovnikov's type of elimination. Okay, then we have our metals that we worked with. So if we're looking with Mg and THF, that's going to prepare a Grignard's reagent. Mg is just going to slide in to where the halogen was, but this is going to, because magnesium is so electropositive, it's going to make carbon electronegative and give you a nucleophile. which you can then react with an electrophile like an H plus or like a ketone or like an epoxide. Okay, CH32CuLi, this is Gilman's reagent, and this is going to act on vinylic or aryl halides, and you're just going to add in whatever's in your parentheses, just one version of that to replace your leaving group. NBS is going to add a bromine to an allylic carbon. There can be carbocation rearrangement with this, I believe, but I don't think it does it as often. And last but not least is hydrohalogenation with a peroxide, which is going to make an anti-Markovnikov's addition of a bromine, which you could see the Br is added to the end, the less stable side. So there is basically every reaction that we need to know.